Welcome back, everyone. We are continuing to study for the regents. This is part 2 of most common topic questions. In this lesson, we will be using the periodic table, so please open your periodic table and let's get started. First question, calculating average atomic mass. If we look at this question, they're asking us for the numerical setup that can be used to determine the atomic mass of bromine. They give you bromine 79 and bromine 81. What you are to do is for each of these isotopes, you are going to take the atomic mass and you are going to multiply it by the natural abundance. But before you can multiply it by the natural abundance, you need to make this percent into a decimal. So now there's two ways you can do this. You can take the number, the percent, and divide it by 100. So 1 divide by 100, or you move the decimal 2 spaces to the left. Decimal 2 spaces to the left. Okay, so for bromine 79, I'm going to take the atomic mass. Okay, so that's 78.92. Okay, I'm going to multiply it by the decimal form of 50.69%. So I'm going to do method 2, which is just moving the decimal 2 spaces to the left. So that's going to be 0.5069. And that's going to be for isotope bromine 79. I'm going to do the same thing for the next one. So once again, I'm taking the atomic mass as I see it, 80.92. I'm multiplying it by the natural abundance, but in the decimal form. So that's going to be 49.31. Now what you do is you add them up. So in this problem, I don't have to solve it because they're only asking me for the numerical setup, and it's a multiple choice. So I'm looking for which one has these numbers. So let's take a look at A. 78.92, that is correct. The 50.69 is what makes it wrong, so I can stop right there. They didn't change the decimal. They didn't change the percent into a decimal, so this is still a percent. I'll stop there. B, 80.92. Okay, that's the atomic mass of bromine 81 multiplied by 50.69. That is the natural abundance of bromine 79. So now what B is doing is mixing up the isotopes, which is not what you're supposed to do. You're supposed to separate the isotopes by the plus sign. So, in other words, what I have here represents one isotope. What I have here represents another isotope. Okay, let's go on to C. 78.92 times 0.5069. All right, that is our answer. Now, we can double check and go to the second part, 80.92 times 0.4931, and that is our answer. So our answer for this one is C, which matches what we have here on the right. Now, here we're given a scenario, and we are to figure out if it's a homogeneous or a heterogeneous mixture. It says, when sample X is passed through filter paper, a white residue Y remains on the paper and a clear liquid Z passes through. When liquid Z is vaporized, another white residue remains. Sample X is best classified as... Okay. This question is giving a lot of things. I'm going to go and read the question one more time and figure out what do they want me to answer. So I'm going to go to the last part where it says sample X is best classified as, okay, so sample X. They specifically want me to say what is sample X, meaning that the Y and the Z I'm not going to put attention to. So I'm going to go back. Sample X is passed through a filter paper. A white residue, Y, remains on the paper. I'm going to stop right there because that gives me enough information to tell me what sample X is. Sample X is being filtered and there's white residue left behind on the filter paper. That is telling me that, well, if white residue was left behind on the filter paper, that means that that white residue did not dissolve in the mixture and that the particle size was too big to pass through the filter paper. Yet, the rest of the mixture, a liquid Z, passed through. So let me draw a little sketch. So let's see, let's say this is the container where the sample is being thrown into. And then on top of the container, there's a funnel. And inside the funnel, there's a filter paper. So let's say this is the filter paper right here. Okay. Sample X is thrown into this funnel. So this is called the funnel. And in this funnel, there's filter paper. On that filter paper, white residue is left behind, and they labeled that as Y. So I'm just going to draw Y's here to represent the white residue. Now, the liquid part passes through, and it's labeled as Z. I should draw this a little bigger. Okay, let me do this one more time quickly. So we got this funnel. We got a container. In the container, we have a liquid Z that went through. And then on the filter paper, we have Y, so the white residue. And this all came from sample X. Now going back to the question, they want you to classify sample X. Well, sample X has white residue getting left behind on the filter paper, while it has also liquid passing through and into the container. So if I label this, well, I can say Z is liquid, right? Because it went through the filter paper and it was small enough to go through. But on the other hand, Y, the particle size was not small enough to go through. So this, I can say this is a solid. It's in solid form. So I see here I have one phase and another phase. So these are two different phases in this mixture. Now, if I'm deciding if it's a homogeneous or a heterogeneous mixture, remember the prefix homo refers to the same, meaning that everything looks the same, it's very well mixed, Everything is well mixed, as in the form as everything has been dissolved. You can't see the different parts. But hetero, on the other hand, means different. So heterogeneous mixture, you can see the different parts because components are in different phases. So this answer would be C, heterogeneous mixture. Sample X is a heterogeneous mixture because we have Y, the residue, in the solid phase, and Z, the liquid that passed through, in the liquid phase. Excited state of an element. So this question is asking which of these electron configurations represents an excited state. The one that represents an excited state, well, we need to know what an excited state means. Excited state means that we're talking about an electron that jumped from its shell to the next. That's what excited means. So, we need to know how many electrons can be held in the first shell and in the second shell. So, in the first shell, we can hold a maximum of 2 electrons. In the second shell, we can hold a maximum of 8 electrons. And I'm going to stop there for now. So, electrons that are in its ground state should look like this: 2 and 8, etc. If I don't see that either the first shell doesn't have 2 electrons or the second shell doesn't have 8 electrons, that means that 1 electron went to the next, and that means that it's excited because it jumped to the next shell. So I'm going to look at these answer choices and I'm going to see which one doesn't either have 2 electrons on the first shell or 8 electrons on the second shell. Let's get started with A. A has 2 electrons on the first shell, so that's good, check. And now it has 7 electrons on the second shell. Well, we know that the second shell can hold a maximum of 8 electrons. So when we see that it has 7, that means that 1 electron jumped to the next shell, and this one represents an electron configuration in the excited state. So A is our answer. The rest, they have the first and the second shell with the maximum number of electrons. So we don't need to worry about any of those. A is our answer. Let's move on to the periodic table. Okay, periodic table trends. Now, the periodic table trends, if you do not have them memorized, that is perfectly fine. You are going to use what the reference table gives you, which is table S. Table S gives you atomic radius. It gives you electronegativity. And it gives you ionization energy. Of all the elements that you have on the periodic table, this question says, as the elements in period 2 on the periodic table are considered in order from left to right, so from left to right, which property generally decreases? Now, if you go to table S and you're saying, well, I don't know how to answer this question. There's just too many things to look at. There is. What you're going to do to approach this question is you're going to pick one element from the left side, let's say lithium, and you're going to pick an element on the right side. Let's say you pick oxygen. The reason you're picking two elements is because you want to zoom in on just two numbers. So compare the number that you have for lithium and the number you have for oxygen and go from there. Because if you look at every single number, you're going to easily be overwhelmed. So if you pick lithium and let's say oxygen or even fluorine, whatever it is, I wouldn't pick a noble gas. And the reason I wouldn't pick a noble gas is because noble gases, we know that they're noble, quote unquote, that they don't bond with other elements. So you're not going to see a value for the electronegativity for noble gases. So I would stay away from noble gases. You could pick any other one. I'm just picking oxygen, for example. You could pick fluorine or you could pick nitrogen, etc. If you go to table S, I want you to look at the atomic radius of lithium and the atomic radius of oxygen. Then you're going to look at the electronegativity of lithium as well, and the electronegativity of oxygen. And finally, the ionization energy of lithium and the ionization of oxygen. You're going to compare those numbers and see which one decreases, because only one of them decreases. Now, periodic table trends. You can either memorize them or, once again, like I just explained, use table S to find your answer. Which one generally decreases? From these answer choices, the correct answer is A, atomic radius decreases. As you go from the left to the right, electronegativity increases, so there's a stronger pull from the electrons, between the electrons and the protons. There's a stronger pull, so there's a stronger attraction. They're getting closer to one another. Ionization energy also increases, so the energy required to take away an electron, that increases, so now it becomes more difficult to take away an electron. And then the atomic radius is decreasing because, well, if the attraction of the electrons and the protons are becoming stronger, then the electrons are being pulled to the protons, which is in the nucleus, and so the atomic radius is decreasing. So that's why A would be our answer. Next one. Dot structures, ion and atom. Okay. So here's a question where they ask you, what is the electron dot structure for this compound? Magnesium fluoride. Now, what you would do for this question is, first, you're going to write the formula. Unless you know how many of each you need, you're writing the formula. So how are you doing that? You're going to the periodic table and you're looking at magnesium and you're looking at fluorine. So I'm going to write it here, magnesium and fluorine. And you're going to look at their charges, their oxidation states. What charges do they have? Because we need to know that in order to write the formula. +2, -1. Circle only the numbers, crisscross, bring them down. So we have Mg invisible 1, right? And then we have F2. So what is this? The formula for this magnesium fluoride is MgF2. Now, if you take a look at the answer choices, we can scratch 2 out from writing the formula. The formula that I just wrote down says that I need 2 fluorines, 2 Fs. A and B only have 1. So A and B can be crossed out. I don't need them. I know that I do not need 1 fluorine. I need 2 for magnesium. So A and B are out. I'm stuck with C and D. Now the electron dot diagram for anions and cations, they're a little bit different from atoms. For atoms, you're not going to use any brackets. For ions, you are going to use brackets. So magnesium, we see on the periodic table, has 2 valence electrons, and fluorine has 7 valence electrons. So I'm going to write it over here. Magnesium has 2 valence electrons, so 2 dots around it, and fluorine has 7 dots around it. Now we both know that all of these are trying to have an octet, meaning that they want 8 electrons. Metals want to give up their electrons. They want to lose their electrons, while nonmetals want to gain electrons. So what magnesium is going to do is give this electron to one fluorine and this electron to another fluorine. Now, let's take care of the magnesium first. Magnesium is losing electrons. So if it lost the 2 valence electrons that it had, now it has no more initial valence electrons that it had before. So the initial valence electrons of 2 are gone. One was given to one fluorine and the other to the other. So after losing 2 electrons, each charge of an electron is a -1. So magnesium, after losing 2 electrons, has a +2 charge. Now, fluorine is no longer fluorine, it's fluoride, because it gained an electron. Now it's an anion. And now this also has a charge. It has a charge of -1. We don't need to write the 1. We should only write the negative, and that's it. So, same thing happens on this side. Okay. At this point, it's very obvious what the answer should be. The answer should be C. One thing I want to note, a little bit of review, for Lewis dot diagrams or electron dot structures, for the anion or the negative charge, you have 8 dots surrounding it. For the cation or the positive charge, you have 0 dots surrounding it. So we see that magnesium has no dots around it, while fluorides has 8 dots around. Okay, let's move on to the next. Bond properties metallic. A solid substance is an excellent conductor of electricity. The chemical bonds in this substance are most likely... Okay, something specific that it says. It says a solid substance. Now, ionic compounds can conduct electricity, but they can't conduct electricity in the solid phase, only in the liquid phase. So A and B are out because this question is asking which is an excellent conductor of electricity in the solid phase, not the liquid. So A and B are out. C and D. The answer is metallic, but now you have to give the correct reasoning as well. So you have to pick which one is giving you the correct reasoning of why metallic is an excellent conductor of electricity in the solid phase. C says because the valence electrons are stationary, and D says the valence electrons are mobile. So which one are you going to go with? Well, if something is conducting electricity, there's a movement of something. And if we're talking about electricity, there's a movement of electrons. For metallic bonding, we talked about sea of mobile electrons. So for a solid substance that is an excellent conductor of electricity, it's metallic because the valence electrons are mobile. So once again, going back to the definition that we talked about when we discussed metallic bonding, which is C of mobile electrons. Let's go to the next one. Percent composition and polyatomic ions. Okay, percent composition is one of those formulas that you do not have to memorize. It is given on table T. I'm going to show you. Table T, it's also labeled. It says percent composition by mass is equal to mass of part over mass of whole times 100. So now I'm going to use this equation. So mass of part, let's look at the question. What is the percent composition by mass of nitrogen in this formula? Okay, so the part we should identify right away is nitrogen. And the reason that it's nitrogen is because it's saying what is the percent composition of nitrogen in this. So the nitrogen is the part, while the whole is the whole compound that we see here. This is the whole. So I'm going to label this, and this is the part. Now, they give you something to save you time while doing this question. They say the gram formula mass, another word for gram formula mass is molar mass. They say the gram formula mass is 96 grams per mole. So, does that represent our whole or does that represent our part? That represents the whole compound. So the gram formula mass that they're giving you is for this whole compound. So 96 represents the whole. So looking at the formula, all you have to do is figure out the mass of the part. Now, since they're asking for nitrogen, I'm going to look at this formula and I'm going to count how many nitrogens do I have. So I have here NH4 in parentheses with a subscript of 2 outside, and then continuing CO3. So this is what I see. I see NH4 parentheses 2 CO3, which is equal to NH4 written twice because we have a subscript outside the parentheses representing that we have 2 NH4 CO3. Now that's the expanded notation of what this compound is giving us. Now I wrote it like this so you see how many nitrogens you have. So now it is very obvious that we have 2 nitrogens. So this subscript here, you multiply it by each subscript that you see. So we have 2 nitrogens and we have 8 hydrogens. Going back to the problem, percent composition by mass of nitrogen in this. So the mass of the part is going to be the molar mass of the nitrogen times 2 because we have 2 nitrogen. So that'll be on the periodic table. If you find nitrogen, you're going to take the molar mass, multiply it by 2, and that's going to be your mass of part. You're going to put that over the mass of the whole, which they give you in the problem, which is 96. Multiply it by 100, and you get your answer. Now I want to move on to the polyatomic ions that were given in this problem. So in this problem, we're given NH4 and we're given CO3. So I'm going to clear my markings for a second. NH4 and CO3. If I go to table E, right, I don't have to memorize these polyatomic ions. Table E gives me the name and the charges of each. So NH4 is called ammonium, and CO3 is called carbonate. Now, ammonium has a charge of +1, and carbonate has a charge of -2. So, table E gives you the polyatomic ion with its charge and the name. I'm going over this because I want to discuss the types of bonds that we see in this compound. So I'm going to write it here. So let me separate it as I see it on table E. So NH4 has a +1 charge, and CO3 has a -2 charge. Well, we know that an ion that is positive charge is a cation. So this is a cation. And we know that an ion that is negatively charged is an anion. A cation plus an anion gives us an ionic compound. So cation plus anion equals ionic. So we can say that this has ionic bonds. Another type of bond it has is, well, if we look at NH4 individually, nitrogen, if we look at the periodic table, it's to the right of the staircase. It's a nonmetal. And H, which is that nonmetal that is on the left side of the periodic table, but it's still a nonmetal. It's the only nonmetal that's on the left side of the periodic table. This is also a nonmetal. So we have a nonmetal bonded to another nonmetal. And what does that give us? That gives us covalent. Same thing for CO3, carbonate. Carbon and oxygen are both nonmetals. So once again, we have a nonmetal plus another nonmetal, which is also covalent bonds. So going back to this formula, we can say that this has ionic and covalent bonds. Moving on to the next, physical or chemical change. A few pieces of dry ice are placed in a flask. The flask is sealed by placing an inflated balloon over the mouth of the flask. As the balloon inflates, the dry ice disappears and no liquid is observed in the flask. Write the name of the process that occurs as the dry ice undergoes a phase change in the flask. Okay, so in this question, they tell us it's a phase change. So phase change, meaning an example of that would be solid to liquid, liquid to gas, etc. So if we're having a phase change, is that a physical or is that a chemical change? Well, that is a physical change because nothing new is being produced. Physical meaning that, okay, the appearance is changing, but the substance itself is not changing. So this is a physical change. Now, let's go on to answer the question. Going back to what they said, we have dry ice, and they tell us the phase of the dry ice. They tell us it's a solid. They say that they put the dry ice in a flask, and then they put an uninflated balloon over it. The balloon inflates, and the dry ice disappears, but there is no liquid left behind. So we're looking at something like this, right? Let's say that this is dry ice at the bottom, and it's disappearing, and the balloon is inflating like you see in the picture. So if there's no liquid, then the solid phase of the carbon dioxide, the dry ice, is going straight to the gas phase. Now, here we are. What is that phase change called when you go from the solid to the gas? When you go from the solid phase to the gas phase, that is called sublimation. So write the name of the process that occurs. The answer for this question is sublimation. Let's go on to the next one. So they give us a table and they say, explain in terms of charge distribution why a molecule of carbon tetrachloride is a non-polar molecule. Okay, so in this problem, they're telling us that carbon tetrachloride is a non-polar molecule. They're not asking us, is it polar or is it non-polar? They gave us the answer already. Now they want us to explain why in terms of charge distribution. So even if you didn't know that carbon tetrachloride was a non-polar molecule, you're going to use that with what the question is giving you and explain, okay, what is a non-polar molecule in terms of charge distribution? You can know nothing of carbon tetrachloride, but if you know how to explain in terms of charge distribution, you'll get the answer correct. So let's get started. For those who don't know how carbon tetrachloride looks like, well, let's take a look at a picture. It looks like this. So the carbon is at the center and the 4 chlorides are surrounding it. Now, in terms of charge distribution, why is it nonpolar? Well, to take a look at it, we have this abbreviation that we are going to use. It's called SNAP. SNAP represents symmetrical is nonpolar molecule, while an asymmetrical molecule is a polar molecule. So we have here the CCl4 drawn out, and now I'm going to explain in terms of charge distribution. Well, I have dipoles drawn here, and they're all pointing outwards, like facing outwards of the carbon. So they're going away from the carbon. That means that the charge distribution is equal. So there's no net dipole in this molecule. Now, another thing you can mention in your answer is, well, it's a nonpolar molecule because it's symmetrical. And in terms of charge distribution, it has an equal charge distribution. So it's symmetrical. Any way you cut it, it will always be symmetrical. And in terms of charge distribution, it is equal. That is all you have to write. Do not write a big paragraph. Straight to the point. If you answer the question, you are done and you can move on. Let's go to isotopes. Isotopes are a big thing in the Regents exams. So no doubt in my mind that it's going to be on it. Which diagram represents nuclei of the same element? Okay. Isotopes. If you don't know what an isotope is, after this, you need to know it. Isotope. You have element, same element, so same number of protons. The only thing that changes is the number of neutrons or the mass number. So, which of these represents nuclei of the same element? Same element, meaning the number of protons need to be the same. So I see D has 1 proton, E has 1 proton, and Q has 1 proton. R has 2 protons, so I'm going to cross out R. R is not one of my answers. So D, E, and Q, they all have 1 proton. Now, do they have different number of neutrons? I'm going to check. D has 0, E has 1, and Q has 2. So they do all have different number of neutrons. So my answer would include D, E, and Q. Moving on to hydrogen bonding. Which compound has the strongest hydrogen bonding between its molecules? Well, hydrogen bonding happens between molecules, and it happens when a hydrogen is attracted to an N or O or F from another molecule. And this N, O, or F needs to be connected to a hydrogen. So let's take a look at these. So HBr. HBr will not have any hydrogen bonding because it doesn't include N or O or F. So we can cross that one out. HCl, same thing, doesn't have N, O, or F. And then we have C and D. C is HF and D is HI. The one that would have hydrogen bonding between its molecules is C, HF. So HF will have hydrogen bonding with another HF. The hydrogen bonding will be this right here, what you see between molecules. So hydrogen bonding, it happens between molecules. So this would be the hydrogen bonding. Let's move on to a mole to mass conversion. What is the mass in grams of 2 moles of NO2? So if you're going from moles to mass, so you are given moles, and you are being asked, what is the mass? Then you need to know what you're going to do with what they're giving you. They give you the formula. They say it's NO2. So you're going to look at the periodic table, and you're going to find the molar mass for each of these. Get the molar mass for NO2, and now you are stuck with, are you going to divide this or are you going to multiply this? Well, the molar mass, the units for molar mass is grams per mole. So if you're starting with moles and you're debating, am I going to divide this? Am I going to multiply by the molar mass? What am I going to do? Go back to dimensional analysis. Set it up. How are the units going to cancel? How are you going to be left with what you need at the end? So at the end, I need the mass, which is going to be in grams. So I'm going to put that I want my answer in grams. And I'm starting with moles. So I'm going to find the molar mass of NO2. And now, once I find that molar mass, what am I going to do with that molar mass? Am I going to multiply it or am I going to divide? Well, I'm going to put it here so we can see. I'm going to multiply the molar mass. And the reason I'm multiplying the molar mass is because now I see the moles on the top and the moles on the bottom. So now I can cancel these units out, and I will only be left with grams, which is what I want. So now this would look like 2 moles, which is what I'm given, and the molar mass that I get for NO2 on the periodic table Well, I'm going to do 14, and then I'm going to do plus 16, plus another 16 because I have 2 oxygen, and I'm going to put that here. Multiply that out, and I will get my answer. Let's go to the next one. What is the number of electrons shared between the atoms in an I2 molecule? Okay, we need to draw the Lewis dot diagram of I2. The way to do this, a little bit of review. Go to the periodic table, look at the valence electrons. Lewis dot diagrams only involve the valence electrons. So, I have 2 iodines. Each one has 7 electrons. So I'm going to put 7 dots around it. Okay, I see that I put all 7 dots around each iodine, and now I'm going to pair the electrons that are not paired, meaning that the electrons that are alone. And I'm going to form a bond between them. So I'm going to circle the electrons that I see doesn't have a buddy or doesn't have a pair to be with. I circled them, and now this is going to look like this. Now that we have the Lewis dot diagram of I2, I'm being asked, what are the number of electrons being shared? So the electrons that you see on the outside so that would be this one, and this one. Those are called lone pairs because they are not being shared. So these are called also unshared electrons. So either called lone pairs or unshared electrons. Okay, now moving on to what are shared electrons. So the shared electrons are the ones that are between symbols. So I have this line that represents the bond that's between the 2 eyes. This bond represents 2 electrons. So 2 electrons are between these 2 eyes. That means that the number of electrons being shared is 2.